chapter 2. In this chapter, we will study the graphs of functions. Okay, the title is Analysis of Graphs of Functions. So we have sketched the graphs of functions in the previous chapter as well. In this chapter, we will learn a systematic ways to study the graphs, analyze them. How can you classify the graphs? Or when you look at a graph, what kind of properties can you observe, and what is the meaning of those properties of the graphs and things like that. Okay, and how can you move the graphs around? When you move a graph to from one place, if you slide it to the left, right, up, down, or if you reflect it, if you rotate it, what will be the equations of the new graph? All of that comes under analysis of graphs. Okay, and this has very important practical applications, and we will also discuss them as we do the word problems. Okay, so let me begin with the first section: graphs of basic functions and relations and symmetry. So in this topic, we are going to look at the graphs of some basic functions, and we are going to look at the um, concept of symmetry in those graphs. Okay, and some properties about that graph which we are seeing in the first page here. Okay, the first topic, subtopic, continuity. So continuity in graphs is literally what it means. If the graph is continuous, it means you can draw it continuously. You can sketch it continuously. There is no break, there is no jump, there is no gap of any kind, continuous, right? So the definition here: a function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without having to lift the pen. Okay? You can draw it continuously. Then the question comes, what is discontinuous? When it is not continuous. That is, we'll study under the topic discontinuities. And it turns out there is not just one, but there are three different ways a graph may be not continuous. The first one, when we get vertical asymptotes. So this occurs when the value of the x, which makes the denominator 0. Okay, so vertical asymptote is, the graph is going to infinity. Now, if the graph is going to infinity, obviously there is a discontinuity, because you cannot draw until infinity, right? The definition is we should be able to sketch it without lifting the hand. Now, if it goes till infinity, either down to negative infinity or up to plus infinity, we have to stop, like, physically we have to leave it at some point, and then assume that it goes to infinity after that. Then I have to lift my pen and start on the other side, right? So vertical asymptote is a discontinuity. And you can see the graph on the bottom right here. Like, on from the left to the right, you have to lift your pen. Okay, so when there is a vertical asymptote, you get discontinuity. And what we are saying here is it occurs when the denominator is 0. Makes sense, right? If the denominator goes to 0, the fraction goes to infinity. Okay, but there is an important rider after that. It says in the reduced quotient form of the function. Not in the original function, but in the reduced quotient form of the function. Okay, and I will explain that now. So for example, you take this function f of x equals 1, not 1, x minus 2 over x square minus 4, let's say. Okay, now the denominator becomes 0. Look at this area, okay? So I'll just write it in for shortcut. Denominator equal to 0 at two places. You get this equal to 0 at x equal to 2 and x equal to minus 2, right? Both at 2 and minus 2, the denominator becomes 0. This is the, by the way, this is a quotient function because there is a fraction, right? A divided by b, it's a quotient function. And the denominator is 0 at x equal to 2 and x equal to minus 2. But do you get vertical asymptotes at 2 and minus 2 both? Okay. For that, let us simplify the function. If you rewrite it, you are going to make the denominator factored. X square minus 4 square is x square minus 2 square. Okay. Now, if you do not, some of you might not remember it, so I'm going to write it on the right side here. The factoring formula. Okay. A square minus b square, okay, can be factored as a plus b times a minus b. Okay. So the x square minus 2 square here can be factored as x plus 2, x minus 2. And once you factor like that, you can cancel the common factors, x minus 2, x minus 2. And what you are left with is 1 over x plus 2. Okay. That is the reduced form. Reduced. So if any common factors are there, those have been cancelled out. That is called the reduced form. Okay. And in the reduced form, you only have x plus 2. You know? That means now, if you plug in x equal to minus 2, it still makes the denominator 0. But, so I'll write here, still works. Okay. But x equal to 2 does not, right? So x equal to 2, that means this x equal to minus 2 has a vertical asymptote there, not a vertical asymptote here. Okay, so at 2 you don't have a vertical asymptote. At minus 2 you have the vertical asymptote. Okay, all right. And that was the explanation about the quotient form, the reduced form, and when you get a vertical asymptote. Let us now look at the graph. Okay, I have taken a simple function here which is already in the reduced form, y equals 1 over x minus 3. That's already reduced, okay, in simplest form, and x minus 3. So that means okay, x minus 3. So that means your denominator is 0 at x equal to 3, right? Okay. Now, because the denominator is 0 there at x equal to 3, you get a vertical asymptote there. The equation of the vertical asymptote is the line x equal to 3. Okay, this is the vertical asymptote. Its equation is x equals 3. Now, don't get confused between two things here, okay? When I write x equals 3 here, I mean when the x value is 3, you get the vertical asymptote. And when I write x equals 3 here, I am writing the equation of the asymptote itself, which is x equals 3. Okay. And while discussing the discontinuity here, a quick we do like on the periphery, we will talk about the domain range, the function when it is increasing, decreasing. Okay, and then we will again continue with the discontinuity. And this is for proper analysis of function. We are analyzing the function, right? So we are studying simultaneously many things. Uh, the domain of this function, check carefully. When we say domain of a function, it includes all the points where it is defined, and you have to just avoid the points where the function is not defined. Okay, and if you see that it is defined everywhere from minus infinity to 3, because there is a discontinuity here, right? Vertical asymptote, it's not defined there. And union, because from 3 to the right it is again defined, 3 to infinity. Okay, and if you wanted to write this in the set builder notation that we used to use earlier, this will be equals x such that x greater than 3 or x less than 3. Okay, so either way, you don't have to write both, write one of them. In both of them, see that we are avoiding the value x equals 3, which is not in the domain. Okay. Similarly, there is one value which is not in the range. I want you to look at the graph. Range means the y values, and figure out what is missing from the range. Okay. And you guessed it correctly. It is the 0 which is missing. Okay. All right. Similarly, decreasing and increasing. If you look at the function is decreasing as you go from the left to right, before the asymptote. Then you take a break, and after the asymptote, it is again decreasing. Okay. So basically, if you see anywhere in the domain, you see the function is decreasing, right? Very interesting here. So I would say function is decreasing on its entire domain. Okay. And it is not increasing anywhere, right? Nowhere. Increasing on nowhere, we can represent that with an empty set. Okay. All right. So we discussed vertical asymptote. A quick review. Vertical asymptote occurs when the denominator is 0 in the reduced form, not just because it is 0 originally. It has to stay 0 after you reduce the function, simplify the function as well. And on the vertical asymptote, those points are not in the domain. And when you draw the graph of a vertical asymptote, the function has to be going to infinity on at least one side. In this case, it goes to infinity on both sides, but it should go to infinity at least on one side. Okay? All right. Next, a hole. That is, there's no vertical asymptote, but there is just a gap. I mean, just a break. So that is represented by a hole. Okay, it's like something is missing. You are continuously going. There's a hole. There's a one point which is missing, and then you are again beginning from the right after that. Okay, that's called a hole in the graph. And turns out this also occurs when the denominator is 0, just like in the case of vertical asymptote. But something should be different, right? And what is that? In the original form, the denominator is 0, but by the time you reduce it, it's not equal to 0 anymore. Okay, so the opposite of what happens in vertical asymptote. In the vertical asymptote, you want it to be 0 in the reduced form. To get a whole, it should not be 0 in the reduced form, but it should be 0 in the original equation. Okay, so let us look at a second example here. Again, I hope you know you're aware of how to do the factoring of that kind of quadratic expressions, x square minus 4x plus 3. If you are not, please refresh yourself, watch some YouTube videos on this or come to me. Okay, if you meet me, we can meet virtually, you can meet in person. I can guide you on that. Okay, but you should be comfortable doing this kind of factoring when you are in college algebra. Okay, so x square minus 4x plus 3 is x minus 1 times x minus 3 over x minus 1. Okay, you cancel that. That becomes minus x plus 3. The minus sign, I distributed it. Or, okay, actually, let me take one step more and show it. So you have minus, and in parentheses, you have x minus 3. Okay. And when you distribute it, becomes minus x plus 3. See? So when the function originally is a quotient function, but when you reduce it, it is just the function y equals minus x plus 3, which we know is a straight line, right? The graph of the equation of a straight line. Okay? We will now look at the graph of this function on the right side of this page. Okay? So the graph that we get for that original function is this straight line, except with the hole there, right? So the function is discontinuous here at x equals 1 because I will write the original function here. It was minus x square minus 4x plus 3 over x minus 1, right? So if you plug in x equal to 1, the denominator becomes 0. So the graph is not continuous there, but it has a hole there. Okay. And the hole occurred at the point 1 comma 2. If you see the graph here. Okay. I'm writing all this because these are the details you will need to know. If you have to sketch the graph of a function which has, hole like that, you need to know where the hole is. Okay. And, your sketching would be accurate if you know that. Okay. And just like before, please write the domain and range. And I hope you can see this more easily now. In the domain, 1 is missing. In the range, 2 is missing. Okay. All right. The other type of discontinuity is called jump. Okay, so when the denominator is 0, we got two types of discontinuities, vertical asymptote and a hole, depending on whether that denominator becoming 0 survived until it was reduced or not. Okay, both of them are discontinuities. Now, either going to infinity or getting a hole. Now, one more type of discontinuity can occur where the function is not going to infinity. There is no hole in the graph. Okay, but there is a break. What kind of break? Some kind of thing has snapped, and things have moved away. So on the left side, you reach a value, and suddenly on the right side, you are starting from a different value. That is a jump. Okay, and you can see in the graph here. And what do I say here? It can occur. Okay, not always, but it can occur with piecewise functions. And we will see the piecewise function an example right below here. The piecewise function, so the function has different pieces, put together, and sometimes the two pieces do not meet, right, where the boundary is, and if they don't meet, you get a gap. Okay, those are called the endpoints of the subintervals. The subintervals are the pieces of on which pieces of the domain, and the graph does not meet at some endpoint. You get discontinuous function. Okay, here's an example. On the right side, the parabola. Okay, this equation here, the third equation is for the right side for x greater than 1, that parabolic shape. It takes you to almost -3 there. Okay, it is defined for x greater than 1, but it is approaching -3 there, right? Before that, the middle interval is the square root function. You can look at the shape. Okay, that is a square root function, and that takes you to the value -1. So there is a jump. Okay, this is the jump or gap. All right. And as I had said, it can occur, does not always have to occur, right? On the other endpoint of that same, middle piece, both of them, the left function and the middle function, they meet at this point. So although there are two different rules, for that, they meet at that point and it is continuous. On the other end, it is not continuous. Okay, that is called jump discontinuity. So I will fill in the blanks now. The function fails to be continuous at x equals 1. Okay. And let us also write where it is decreasing and increasing. The function y is decreasing, if you see from the left, from -infinity until it reaches the value -3. Okay. Now from -3 to the right, it is increasing. Okay. But be careful. Can you say it is from -3 to infinity? It is increasing and increasing continuously, right? If you write -infinity to, sorry, from -3 to infinity directly, that would be incorrect. Okay, because if you look at the two pieces, at 1, it is going up and then suddenly you start from a lower value, right? That's not increasing. You have actually decreased. So how you should put it? But at the same time, you don't see an interval where the graph is actually decreasing. So what you do is you divide into two intervals. -3 to 1, it is increasing. And again, it is increasing from 1 to infinity. Okay. And similarly, and this function, we are discussing many important concepts. Okay. What is the domain and range of this function? Okay, give it a try. Important for conceptual understanding, is what I have given the title for it. Look at the function and try to figure out what the domain is. And if you have paid, pause the video and given a thought, you would have realized the domain is the entire real numbers. There is no value where it is not defined. Okay. And I want to emphasize here, in the previous cases where there was not continuous, that value was missing from the domain, right? It's the whole, that value is missing from the domain. When there is a vertical asymptote, that value is missing from the domain. In the case of jump or gap, that is not necessary. Okay. Because when there is a jump or a gap, we are not saying that that value should not be in the domain. Okay. And you might wonder, we see a hole in this graph here, but actually the hole is for one piece. But if you look at the function, the middle piece also is a part of the function, right? And that is defined at 1. There is a field, the solid circle for the middle piece at x equal to 1. Okay. So for the function as a whole, it is defined. The function has a value at 1, which is minus 1. 1 comma minus 1 is a point on the function. Therefore, the domain is the entire real line here. And if you look at the range similarly, the lowest value you go is -3, right? And if you look at the right side piece, the piece on the right end, -3 is not included. It doesn't touch -3. It gets close to it. But on the left piece, where the two things meet, the -3 is reached, right? They meet at -3. So -3 is included. And then all the way till infinity. Okay. Similarly, the same graph, we will look at the concept of continuity once more. Okay. So in the proper language of continuity, we will say this. Okay. When you look at that graph, you will say the function is continuous on each of the intervals -infinity to -3, -3 to 1, and 1 to infinity. It is continuous in all those intervals. Okay. In each piece, it is continuous. And now when you look at overall, there are two boundary points, 3 and -3 and 1. At -3 and 1, the rules are changing, right? But among them, at -3, it is still continuous because they meet. But it is not continuous finally at x equal to 1 because at that endpoint, there is a gap. Okay, that is the full picture, about the continuity of this function. Continuous on each subinterval, and at the boundary points also continuous at one of them where the two pieces will meet, and not continuous at the value where the two pieces do not meet. All right. Okay, so I will only do this one page in this video because these are heavy concepts. Make sure you fill the notes and understand the concepts properly. Rewatch the video, watch some more video if you need, okay? But make sure you have fully learned this, okay? Then in the next video, we will do some problems and other concepts. See you.